Okay, good afternoon. Let's get started on the afternoon session here. Looking forward to discussing a little bit more emerging technology, and but still highly related to the topic of concrete. I'd like to introduce the first group of speakers, Brian Ellis and Victor Lee. Brian Ellis is an assistant professor in the Department of Civil and Environmental Engineering at the University of Michigan, and his research focuses on the development of safe and emerging energy technologies. And Dr. Victor Lee, who I've worked with for many years, is the James R. Rice Distinguished University Professor of Engineering and the E.B. Wiley Collegiate Professor of Civil Engineering at the University of Michigan. His research interest is in multifunctional materials targeted at enhancing civil infrastructure, sustainability, and resiliency. He led the research team that invented engineering cementitious composites, popularly known as bendable concrete, which I think you will see some exciting pictures of in this presentation. So let's welcome Victor and Brian.
So you should be able to advance the slide, I think.
Yeah.
All right.
Okay, so talking about concrete innovations, it might be good to get started with some historical background, how concrete has been developing. Where is it? There, okay. All right. So going back all the way to 3000 BC, we have the Egyptian pyramid, and of course later on we have the Roman structures. Those are the pre-modern day concrete, perhaps using the invention of Portland cement as the defining line for modern day concrete about 200 years ago. And the first concrete bridge in California, first concrete road in Ohio, not that far from here in Michigan, and the first tall buildings made out of concrete, and marching forward, the Edison homes that are built out of concrete, and the first ready-mix truck, and then the Hoover Dam, which is still standing, of course, and finally to today, we have the tallest building and the longest bridge in the world made out of concrete materials. Now, throughout this whole period, the modern day concrete, about 200 years or so, concrete strength has been rising continuously over time so that we can build bigger and longer things. But what is in the future for us? What do you think, Brian?
Well, I think we need to be motivated first by asking ourselves why we need concrete or innovation in concrete. So we've already seen this a couple times in different ways. What we're looking at is the increase in global temperature over the past 50 or so years. And what I want to point out in this graph that's most critical is if we want to avoid the critical temperature rise of 1.5 degrees Celsius, and we used to operate on a 2 degrees C, that's actually been lowered down. If we want to achieve that temperature, we need to act now. There has to be innovations in materials such as concrete, which coupled with building energy use, it accounts for almost 40% of global CO2 emissions. And so this is really, the take-home message from this isn't trying to understand what trajectory we're on, but it's to really hit home the fact that there's an urgent need to find innovative strategies right now to address the global climate change related to, by and large, CO2 emissions. And we know that climate change impacts are happening, right? So just a couple months ago, we were seeing devastation of hurricanes in the Bahamas, and we see these events taking place more frequently. You know, you might have heard about 100-year floods, right? We're having 100-year floods every few years, right? So this is an opportunity where the whole society is being affected and actually seeing these effects of climate change. And currently, right now, we have the fires taking place in California. But climate change does not just mean everything gets more extreme or drier. It just means that you have wet events or dry events that happen in greater extremes and greater frequencies. So there's going to be parts of the world that are going to be experiencing drought, while other parts in the world are getting flooded in extreme events, such as shown here in these pictures. But what we're really focused on, and this is trying to motivate some of the work that we're going to talk about here, is that we see that this is obvious to the younger generation, right? This recent climate strike. What you're seeing here is people out protesting, saying we need to attack this now, right? And so one of the things that we're trying to think about is how can we innovate in the world's largest consumed material, concrete, such that we can address the climate change problems.
So climate change is here. What we need to do is both adapting to climate change as well as try to mitigate it. And coming back to concrete, what I see is that we need pervious concrete. We need concretes that are much more resilient, or infrastructures built out of concrete that are much more resilient to extreme forces, fire resistance, self-thermoadaptive materials that are smart, not just carrying load, but being able to respond to the environment. And mitigation strategies like greener cement, carbon sequestration in concrete material, I'm sure you have heard a lot, and even self-healing concrete that allows the material to be much more durable and require less frequent repairs. Okay, so if you ask me what is in the future, I would say, how about concrete for climate change, CCC? So the transformation that I'm seeing into the future is concrete has to transform from being a brittle material into a ductile material, ductile concrete. I know it doesn't sound very smooth in your ear. For some people, this is obviously an oxymoron, but let's move on a little bit. Okay, the second transformation that I observe also is that we need to make concrete that goes from being dumb, just low carrying, into smart material that responds to the environment. And we need concrete to be green, and I already mentioned carbon sequestration. We need concrete that are able to allow us to build efficiently. Okay, 3D printing that I'll just mention at the end, but the next talks will also talk about that. Okay.
So thinking about how we can treat this as a conversation, Victor's now going to take a chance to tell us how we can build more resilient material, or how we can innovate in our concrete materials to make more resilient infrastructure.
I'm more used to giving a talk myself. So we are practicing trying to communicate and make a conversation out of this. But we are not professionals. All right, so how to make infrastructure more resilient, concrete more resilient, more damage tolerant? We need to learn from nature. Now let's see if this works. Okay. So nature tells us that you don't really try to resist by being strong. You need to sometimes relax and give. And willow trees is like that. So these willow trees are very hard to be blown down by strong winds. They are stronger than actually very strong oak trees. They are more difficult to pull it down because they are resilient. They have a give. When strong winds blow, they just let go, and the wind forces pass by. In fact, this idea has also been used in materials created by nature. What you're looking at here is the nacre material, the iridescent color material called nacre, on the inside of abalone shells. And these materials are built out of something very close to cement, like calcium carbonate, equally brittle. But when you test nacre, it's actually more like a metallic material. So they can undergo plastic yielding. How about that? Turning chalk-like material into a steel-like material. And nature already have done that. How many of you know why nature do this for nacre inside the abalone shells? Survival, of course. The abalone doesn't want to be eaten. Okay? Sea turtles is their enemy. Sea turtles can break the shell. And so what the Abalone tries to do is to protect itself, its body, by having this kind of material which is ductile, very difficult to break them. So we copied the idea of nature. We borrowed this idea, and so we can see here concrete that is brittle, high-strength concrete, okay, can break very easily, fracture into two pieces under a bending load, whereas we can make AECC material a new type of bendable concrete that can undergo large amount of deformation without breaking into two parts. And the trick is actually creating internal mechanisms for the material to give, as opposed to resisting the force by not moving at all. Okay. So this material is no longer an academic curiosity. It's already gone out into the full-scale application, including, for example, this building, this picture I took myself. And the material is used in these coupling beams, illustrated here as the yellow portions here. The material is used to keep the building safe and resilient under extreme load. That building is in Japan in a seismic zone. So the material is developed and has gone out into the field applications. Now, not only is the material resilient, but we can make the material self-heal. And let's see if this video works or not. Hopefully it does. So this is a piece of the specimen that has been deliberately damaged in a machine, and it's exposed only to air and water. And you can see that the material can undergo self-healing. So the analogy here is that it looks very much like my paper cut on my hand. That's a photo of my hand. Just happened that a graduate student came in when I had, ouch, and I say, take my picture. And there it goes, right? So if you have paper cuts, biological material, my hand can repair itself. Okay. If I have a chainsaw that goes through my hand, obviously that doesn't work, right? So unfortunately, normal concrete is somewhat like chainsaw cuts. The crack widths can be quite large, millimeters even larger. But in ECC material, these damages, even when you strain it to that bent out smiley face shape, these microcracks are self-controlled down to less than 50 microns. How large is 50 microns? Our human hair is about 100 microns, so it's very, very thin, almost invisible to the eyes, to the naked eyes. Okay, this material, apart from self-healing, it can also have this self-thermal adaptive behavior. And what it does is that it can include phase change materials so that when the outdoor temperature rises and the heat is trying to get into our homes and we are about to turn on the air conditioning, then you see the thermal capacity jumps, okay? And it actually blocks the heat from coming into the interior of the home. In this way, we use the material as a means to reduce energy usage and reduce carbon in the use phase of the material when the building is operating. So this kind of material, for example, has been tested in this chimney. This is a home in Ann Arbor, and it's a technique where we combine both passive design and this advanced material, and it turns out that we can decrease the temperature by about 5 degrees and delay the peak temperature by about 2 hours. So the material is resilient, it's durable, it self-repairs, has lots of smart functions. And coming back very close to climate change, let's talk a little bit about, can we make it really super green, Brian? What do you think?
Well, I think we can. All right, so we're going to have confidence. But one of the things that, so we just heard about how we can tune the material to be more resilient, maintain crack width, self-heal, potentially provide better heating and cooling for a building. But how else might we be able to change the way we make the material to actually turn it into a greener product, right? And so this is directly looking at opportunities to sequester the CO2, whether it be from fossil fossil fuel power generation or from the actual making of the cement itself. As we heard earlier, the cement industry accounts for about 8% of global CO2 emissions. And so we're pursuing some work, and there's others also looking into this, where we're actually looking to take advantage of that CO2 and put it back into our concrete materials. Now, this is somewhat counterintuitive to what we heard at the start of today's session, where we basically learned that CO2 ingress eventually can lead to loss of alkalinity in the material such that you get corrosion of your steel reinforcement. In our case, we're taking advantage of, for example, the ECC, which does not necessarily require pre-stressed steel reinforcement, and we're utilizing CO2 from point source emission sites and directly incorporating that into the manufacture of a precast product. And as shown here, this is, I think, where's my pointer? We have a project right now where we're actually going to be building precast ECC carbonated railroad ties. And this isn't a picture of our chamber, but we just found out today our chamber is finished. And this is a 12-foot long, 4-foot diameter autoclave where we're able to pressurize and carbonate materials under controlled conditions. And in this case, we've actually demonstrated at bench scale that we were able to store 30% of CO2 by cement mass. Right? So you're taking a CO2-intensive material and greening it by actually pushing it back towards calcite production. Also, you can have the opportunity to do cast in place. So cast in place, this is where you poured foundations or roads. This accounts for 70% of the concrete market. Right? So we have to look at new opportunities to incorporate CO2 here. And one of the things that we've examined is actually carbonating waste materials ahead of time and then mixing them in directly with these cast-in-place applications. And this is an opportunity to take care of waste that has no other value while also directly incorporating CO2 and effectively using this as aggregate. And in the end, we hope to be able to do this in a way that utilizes a waste product and generates a longer, more durable concrete product. Right? So we're looking to have a balance between use, so like the usefulness of the material and its longevity as an infrastructure component, and effectively close the loop where we're even considering opportunities where you can create these carbonated ECC materials and then reuse them, reconfigure them. At the end of the day, trying to treat CO2 as a resource and not a waste product just associated with the production of concrete materials. But the question I have for Victor to end this discussion is, if we have innovation in material design and applications where we might be able to utilize waste products, where are the opportunities to innovate in the actual manufacturing of buildings?
So, many of you have heard of 3D printing, and it's not difficult to imagine, however, that 3D printing of concrete structure is a challenge in the sense that concrete being brittle, after 200 years of development remaining brittle, it requires steel reinforcement. But the placement of steel reinforcement and the 3D printing process are incompatible. It's very difficult to make both of those work together in an efficient manner. So how about if we 3D print bendable concrete that is self-reinforced without the need for steel reinforcement? Can we really print such material? And the answer is, yeah, maybe, if I can turn this here. So this is work done, collaborations between the School of Architecture and the Civil Engineering Department. Using a Cooker robot, we are able to print, and let's see if I can activate that little movie here. I apologize for the shading there, because there is some innovations here which are being patented, and we were advised not to show this publicly, otherwise it destroys the patent application. But you can see here this ECC material being 3D printed into a wall panel for building applications. Okay. So given the fact that we have limited amount of time, so I'm going to come to a conclusion. So we started off with this discussion with whether we can create new innovations in concrete that is suitable for climate change adaptation and mitigation. And I would say that such material do exist now. Okay, so we don't really necessarily have to wait for the future. Of course, there are further development work that can be beneficial, but such material is available, and as you saw, can be put into full-scale structures. Okay, and in terms of architectural appeals, apart from resiliency that we talked about, there are also the possibility. I believe that earlier this morning there was a talk that mentions corrosion of the reinforcing steel as a challenge to deterioration of reinforced concrete structures. In this case here, because we are using a self-reinforced cementitious material, at least the steel that is typically used to control cracks will no longer be needed. Okay? We may still need to use structural steel, but the steels that are used to control cracks we may not need anymore. Now, if we can get rid of that type of steel, then they cannot corrode because they are not there. So that becomes an elimination of a major source of infrastructure decay problem. Okay? So with the removal of the steel, we can also lightweight the structure. They already mentioned that the material is 3D printable, so it supports automation and construction efficiency, building faster and better with this kind of material. Our concrete construction industry is not the most efficient one. The productivity actually is lagging behind the general economy by a factor of 7. So anywhere we can improve construction efficiency and build faster would be welcome, I believe. Okay, so ultimately, what we are aiming at, of course, in the development of such materials is to create stronger harmony between the built environment and the natural environment. I don't believe anyone would argue that we need both of them. We just want to make sure that they are harmoniously coexisting. Okay, so is everything good and everything's done? I would say no. There are still challenges, including earlier discussions about codes and standards. We are in a relatively conservative industry, and reliability or liability can become obstacles to innovation. So these are work that we still need to do. We need further R&D in education and training, and there is a lot more that we can do that goes beyond the materials, but into the design of buildings and other types of infrastructures, their construction, their operations and maintenance, and end of life. There's a lot of opportunity where we can cut carbon emissions throughout the life cycle of our infrastructures. So we need to exploit this. And just to put in a plug for a center we are building, so this is the Center for Low Carbon Built Environment. We're just starting up. I see my time is up. But so those of you who are interested, you're most welcome, and we can chat afterwards. Thank you so much. Thank you.
So next we're going to continue along this theme of innovation, but explore potential applications outside of our planetary boundaries. Michael Fisk currently serves as the Jacobs ESSCA Technical Fellow for Advanced Materials and Manufacturing. He has over 30 years of experience in design, development, fabrication, and testing of unique material processing hardware. This encompasses ground and spaceflight hardware, rocket engine assembly and test, additive manufacturing, and most recently additive construction. He's joined by Shadi Nazarian. She's an associate professor at the Stuckman School of Architecture and Landscape Architecture at the Pennsylvania State University. Her research focuses on novel material and production processes, specifically 3D printing with functionally graded materials, which enable the concept of a seamless architecture. Thank you.
Glad I got that out of the way. Thank you for having us. This is a novel venue and opportunity for me to see what's going on in the rest of the world. I'll start by saying that in 2004, I was asked to lead a team aimed at development of in situ-based infrastructure elements on the moon. Roads, landing pads, habitats, shelters, etc. These structures were all to be built autonomously. They were to be built using nothing but the material that was available on the moon with hardware that we would deliver to the moon. And we've been looking at these technologies pretty much ever since. Jump ahead to 2015 maybe. NASA sponsored a 3D printed habitat challenge that was a multi-year, multi-phase challenge. I was one of the judges. Dr. Shadi Nazarian led one of the teams from Penn State. That's where we first met, and we've kind of been collaborating since that, after the competition was over. So we had several conversations between us about how to do this, and in the process of doing it, we asked each other a lot of questions, and we thought the way we would handle this today was basically to duplicate some of those conversations and see how that worked. So the first thing I'd like to ask Shadi to discuss is, from her perspective, where does the focus between aesthetics and function change to one of primarily function, or does it? So.
Sorry, I'm trying to start this.
I don't know.
There it is.
Click right there, yeah.
Use the mouse.
Yeah.
Oh, right, okay. Sorry, I don't work with PCs, so I'm a little lost here.
Oh, you're good. It's on the screen.
Oh, okay. So, great, thank you. So before I talk about the project, for which I actually didn't bring much images or didn't include many images in the PowerPoint, but there is a poster later on that has some more information, perhaps. I want to explain the research approach that Penn State team has taken. We have a transdisciplinary team of 6 faculty and many, many students. So at any time, we have about 20 people working. What we have decided is to think about what 3D printing makes possible. We were not interested in doing things that already were available or possible by doing conventional construction. So, for example, we decided no formwork. Even though 3D printing, in fact, is free form, many people are creating or printing the formwork and then pouring concrete inside. We wanted to stay away from that. Then we decided no assembly of parts. We were interested in monolithic structures, and I'll explain that a little bit more later. We also decided no support structure, which meant that we needed to study the maximum angle at which we could print, and no prefabricated parts, meaning we weren't interested in using any skylights or build walls and then finish it with a typical or conventional roof structure. We were interested in actually exploring how we can complete the structure totally built using this technology, enclosure and all. And also, we're not interested in mass production, but mass customization and automation. And that's something that when we joined NASA 3D Printed Habitat Challenge competition in phase 2, we had to engage automation, even though we weren't much advanced at that point. But the competition actually helped us to facilitate and speed us up. Also, we had to think about deployment of the technology and building on harsh conditions and difficult sites, such as Mars. we realize that this results in a transforming language of architecture. It is unavoidable. Every time there is a new technology, architecture responds and pushes that new technology to its boundaries. But this causes a dialogue between that new technology and architecture. They're both affected. And we also recognize that 3D printing or additive construction is a disruptive technology, which means that it really sets in motion innovation of multiple different types of things. So the answer to your question is we never stop. That the relationship between material investigation of materials, printing systems, and design is ongoing, and all the time there is no point at which we would stop designing and start thinking about material. It's always everything all at once, and they are related, interrelated completely. So we model complex relationships between the variables. We look at the affordances of the additive construction technology in terms of form and structure to determine the impact on design, but also what we want to design, how could it impact the development of technology. We want to be at the table where materials are designed and developed, where technologies are designed and developed, and as well as systems. We're also interested in aesthetically pleasing and spatially uplifting environments. So for example, in the Mars Habitat Challenge competition, we did not want anything that is claustrophobic. One of the emphasis in the design of the habitat was to create tall ceilings and environments that felt good to live in. So the design of the material, for example, the material needs to be flowable through the hoses. It needs to set quickly enough once it's deposited so that it holds its own shape and also takes the weight of the following layers. The system, from everything from end effectors, the manipulation of the reach of the robot, mixer, pump, everything is constantly being designed and altered and hacked. The architectural design is informed by the technology, but also informed by the history of architecture. Where, for example, we look at masonry construction techniques such as corbelling, specifically where there is no mortar, so mortar-less construction of units, modules, building modules. We also explore to achieve articulated and intricate surfaces that are articulated well, and also spatial quality. So these are all always at the table. So we work with these goals for projects on Earth as well as on Mars because of the competition. And I'd like to ask Mike to expand or speak about how the lunar environment provides the drivers for concrete construction.
Thanks. So as I started working with this team in the early 2000s, and we were looking at, by then, 3D printing of concrete was becoming known in the community a little bit, and we realized pretty quickly that if we printed anything on the lunar surface, and we wanted to print because it was a very, it was a process that looked like we could automate it, we weren't going to be printing Portland cement-based materials. There's no carbon, there's no, very little sodium to speak of, there's no clay. And we were tasked with using in situ materials. So we started looking at other materials, which I'll talk about. But the primary material available to us is regolith, lunar regolith. Regolith is a term, another term for soil, but in this case, it's soil that has absolutely no organic matter to it whatsoever. It's very, very fine. You probably, those of you who remember the Apollo days, it's very fine powder. It sticks to everything, primarily because of the agglutinitic structure that you see up on the upper right. It's a very jagged, very cohesive structure. These particulates are on the order of 10 microns, and they are several meters deep across the surface of the moon. The composition changes a little bit between the highlands and the mare. But this is what we have to deal with. So when I start looking at a a composition for a cement, for example, all I have available to me is this. I can melt it and see what I can extract from it. I can run it through various processes like ionic liquid selective extraction. And then I can use the regolith itself as the aggregate for the concrete. So before I really begin to talk about the environment, as a little segue into this chart, I want to ask everybody here if you're familiar with the fact that there's a new restaurant on the moon. Anybody? The food is great, but it has no atmosphere. So there's another show at 6 if you guys want to come back. So tell your kids that. They're going to love it. So that's the main thing everybody thinks about on the moon. There's no atmosphere. It's dusty. It's a hard vacuum. Large temperature swings, both the equator and the poles. Significant. You think about concrete withstanding some of these temperature swings, and it's a real problem. Very long days and nights. I mentioned the dust. Very sharp, angular soil. I've got it right here in front of me. Very sharp, angular soil with a high angle of repose. You can dig a trench with almost vertical walls about 3 feet deep and it won't collapse. But in the process of doing that, you'll tear up your shovel because it's incredibly abrasive. And you'll notice, well, those of you who looked at any lunar history, when they were trying to dig probes to do prospecting on the moon, it was much harder to dig deep than they thought it would be. And they're having the same problem on Mars now. The solar flux is the same as on Earth, but there's no protection from any atmosphere to the radiation environment. So solar, GCR, galactic cosmic radiation, and single or solar particle events, are prevalent and very dangerous to hardware. So everything's got to be in a garage when it's not out, or shelter when it's not exposed. The moon is much more seismically active than we thought it was. Between 72 and 77, there were something like 28 earthquakes detected by the Apollo seismometer network that were 5.5 Richter scale. The problem is there's no dampening by the soil. So an earthquake on the moon might ring for 45 minutes to an hour with significant movement that we would have to deal with any kind of a structure. And I think I mentioned the environment. And lastly, the impacts of this environment to concrete construction are significant when you look to both the hardware that we're printing with and to whatever structure we're building. You can see these are two of the structures. The upper structure there is the one built by Penn State at the head-to-head competition in Peoria. The lower one was built by a company called AI Space Factory. The gantry-style printer in the middle picture there is one that we built at Marshall Space Flight Center. We delivered it to the Corps of Engineers so they could print barracks for their troops, bridges, other anti-tank obstacles, et cetera. That's about 50 by 30 by 20 feet tall. And the lower left there is just my artist's rendition of what a habitat on the moon might look like, and I'll show you that in a moment. But as we started looking at some of these structures, we began to realize that, when you talk about natural light, for example, even on the moon, you'd like to get natural light if you can do it in a way to protect crew members and hardware. And I was intrigued by Dr. Nazarian's proposal to NASA when they submitted it, that she had a background with studying functionally graded material. So I'd like to ask Dr. Nazarian to talk about some of her research in that area and potential impacts to habitat structures.
So this is an area that I'm quite passionate about. When I first joined the faculty at Penn State, within the first few weeks, I approached material scientists with a vision. I wanted to create a seamless joint from concrete to glass, meaning imagine, for example, where you have a wall and there's a glass window. There are so many tiny little details and mechanical joints to bring the glass inside the concrete wall. I wanted to avoid that frame if you don't need to operate that window. So also, in today's construction technology, we have multiple layers inside the wall, and I wanted to also somehow think about how to avoid those, to simplify the very, very complex system that we have created for ourselves to join materials and to join building elements. So I wanted to avoid the complexity. And so it took us several years, but we did create the joint. So we invented a joint between a particular kind of concrete, geopolymer concrete, which is far more environmentally friendly than the Portland cement concrete. So we created this joint not only bringing the two materials together. By that I mean clearly no mechanical frame or adhesives, but truly when you look at it with scanning electron microscopy, you do see that these are united. And also we were able to achieve it in a graded fashion. So imagine if you were walking along a wall, the wall gradually transitions from opaque to totally transparent. So you could place structure where it's needed. You could place opacity or translucency where you would like it. And the other thing that was actually a surprise but very interesting learning experience for me was that these two materials are actually from the same family of materials. They're both ceramics. So to achieve this union, I had to raise the temperature in my furnace to about 950 C, which means it is a little bit difficult to make that happen at architectural scale, but we are looking at different techniques of sintering. So the positive things are that it is impermeable, this both along and through. No water, air, gas, nothing goes through it. And also we have functionally graded material from cork to, with cork. This explains a little bit of that. And I'd like to ask Mike to come back and talk about the advancements of how to configure Mars, lunar concrete, right?
Thank you. So as I mentioned, when we started this, everything I knew about, I'm a metallurgical engineer by background, so everything I knew about concrete was on the side of a bag of Quickcrete. And so the first thing we did was get out there and start playing with ordinary Portland cement-based materials, but we started adding lunar soil simulant, or lunar regolith simulant, and Mars regolith simulant to it, and try and develop compositions that we could still pump through our printer at Marshall. The results of that are shown on the far left there under standard mix. Well, no, I'm sorry, let me correct myself. Standard mix is basically a mortar with with very, very small aggregate in it, but it's just sand. The Mars simulant column and the Moon simulant column are OPC with the respective simulants added as the aggregate. We then began studying MgO-based cements with limited success. We have what we call a CAN cooperative agreement with the University of Mississippi, and they're continuing to research for us on MgO-based cements. There's a number of magnesium oxysulfate, magnesium oxide, magnesium chloride, the Sorel class of cements. But the work that we did at Marshall, we got fairly low strength, as you can see by that red bar, which barely met our threshold. With the when we started looking at CSA mixes, calcium sulfoaluminate concretes, we had a lot more success. We're able to, they're fairly rapid setting. We're able to temper that set with additives and still be able to print without significant cracking and with good flowability through our pump. And you can see the compressive strength is fairly high for those CSA cements. And we actually have samples of those now that are just being launched. You probably heard that the X-37 just landed in California. They fly an exposure experiment in support of NASA, and we have samples of most of these cements that are flying on the next version of the X-37. So it'll launch at a TBD time. They don't tell us till afterwards. It'll be up somewhere between 9 months and 2 years, and then we'll be able to get the samples back and see how they withstood the atomic oxygen environment and solar radiation. So these are a number of the concretes we've looked at. We've been able to demonstrate that you can take regolith simulant and melt it, and we can pull fiber from that. It's a very glassy material. Approximately 60% of lunar regolith is oxygen tied up in various metal oxides. We can pull a very glassy fiber from that. We can chop that fiber up and mix it with the concrete material as we're casting it as reinforcement. We can also cast it into molds and use it as actual rebar. It's a lot of work, and there's not a lot of regular simulants, so we have to be very judicious in how we use the simulant for these tests. We're also looking at sintering the regolith itself on the surface as a potential for roads and landing pads. We know we can print a concrete structure, but I don't know if a monolithic structure will be able to survive, say, the engine thrust. And let's see, I think I have one more chart on this. Yeah, we can also extract water, we know, and use that in the binder. But if we use water in our binder, we're going to have to provide some kind of overpressure over the printer as we build a structure, just because the water will try to come out of the concrete and it'll turn into a big muffin. We've done it. Voice of experience. The water that's trapped in the shadowed regions of the craters, we refer to that as icy regolith. It's even harder to excavate than the normal regolith. The density of the regolith goes up with depth, and it's very difficult. And you can imagine the only thing you have working to your advantage in excavation is mass. And that's why you see, excavators are typically huge, heavy structures, but we can't put that on the moon. So we have to be able to excavate very small amounts, but for a long time, so in order to offset the cohesiveness of especially the icy regolith. And we're also going to be competing for water with life support, propulsion applications, and potentially other construction applications as well. So with that, we'd like to show a 1-minute video, I think, that was at the tail end. We're going to have to skip these. Okay, well, how do I run that? Just hit the green button?
No, it's next one, not this one.
Oh, well.
Go ahead.
Oh,
And
sorry.
after that, all right.
Use the mouse?
No.
All right, that's it. Thank you very much.
Okay, so moving on to the last presentation in this session, I want to introduce Vineet Kamat. He's a professor and the John L. Tishman Faculty Scholar in the Department of Civil and Environmental Engineering at the University of Michigan. He directs the Laboratory for Interactive Visualization and Engineering and co-directs the Construction Engineering Laboratory. His research is primarily focused on virtual and augmented reality, visualization, simulation, mobile computing, robotics, and their application in construction. And I'd also like to introduce Matt Hedke. He's the Senior Virtual Design and Construction Manager at Barton Malow. Matt's been with Barton Malow for 19 years, holding a variety of roles from rebar detailing, estimating, project estimator, detail estimator. Before now, his current role is Senior VDC Manager. In his current role, he's focused on how Barton Malow leverages technology to improve quality, safety, workflow efficiency, and field productivity for all the trades. Thanks.
Thank you.
Just keep going. Okay. Thank you, Wes, for the kind introduction and for giving us an opportunity to speak here this afternoon. So Matt and I met for the first time in our life 5 minutes ago, so I hope this is worth your time. I'm just kidding. We've been in touch for quite a while. So we're going to talk a little bit about robotic construction and some of the current work that has been going on both in the research spectrum as well as in the field, and try to blend our perspectives along the way. And I'm going to begin with a slide that many of you folks may have seen in one context or the other, and that represents the fact that even though there is some debate on how you measure productivity in construction, there is general consensus that productivity in many other industries has consistently gone up over the years, but construction is at best stagnant or maybe going down a little bit. And since we are talking about concrete construction, we thought it befitting to see how concrete construction looked like historically. So here we have an old picture courtesy of a friend of mine at NIST about concrete being poured at Somerset Dam. This was before my dad was born. He was born in 1939. And then this could be this building maybe a few years ago. And as we can see, not much has changed, right? So things are done pretty much the same way. Concrete is poured, handled, managed in the field pretty much the same way as well. And even though construction in the field per se, and concrete construction in particular, is a good candidate for what we call the 3 Ds, meaning like dull, dirty, and dangerous work. The question really is, why is field construction, particularly as it relates to concrete, like this today, and maybe not something like this, right? So from my perspective, and Matt will share a few things on this as well as we go along, there are a few key reasons as to why we don't see a predominance of robots on construction sites, or you may say in concrete construction. And generally speaking, I think we all agree that each project is unique and in many cases expression of the designer's or architect's intent for that particular situation. From a more technical perspective related to deployment of robots, it's very difficult to put any kind of metrology or sensing system on a site that can track a robot, make it do useful work in a mobile context. So the environment is rugged, cluttered, dynamic, and unstructured, meaning the folks who work on a site generally know where things are, but it is far from a controlled environment in the sense that it's not a situation where a robot will find what it needs at the place it expects. So that's why we call it a slightly unstructured environment. Another important issue is something called tolerance stack-up. So unlike a manufactured product, tolerances in construction are relatively weaker, and it's that much difficult for a robot or any kind of automated process to do useful work when there can be discrepancies between what is designed and maybe slightly what is built is slightly different from that design intent. And last but not least, in a typical factory, the general idea is the worker or the robot stays fixed to their location and the work comes to them. In construction, particularly on site, generally you need, even if the work is repetitive, you need to go to that place to do repetitive instances of those. And I think that causes quite a bit of complexity for deployment of robots. Having said that, though, there are quite a few instances where automation and robotics has been successfully deployed on construction sites or in other factory type of settings. And we are going to focus particularly on 4 aspects of concrete construction and integration of robotics within that context. First, we are going to talk about prefabricated concrete manufacturing, then talk about some work that has been done in on-site concrete construction, talk a little bit about retrofitting concrete structures after they are initially built, and finally wrap up with some thoughts about cutting-edge work that has been going on, including 3D printing that we have been seeing extensively here. So let me briefly begin by talking about prefabricated concrete manufacturing. I think this primarily has stemmed from advances in precast construction, the idea being that if you can manufacture concrete elements in a factory-like setting the environment and therefore the quality of the product can be better controlled. You can have more consistency in the units that are produced. And the problem is then reduced to taking these units to site and assembling them in some way. I'm not an architect, but I would assume this may restrict some expressiveness in the form of design, but it does offer many other benefits of modular construction. And I know this is something that the industry also looks at quite closely. So I'm going to start to begin a conversation here with Matt myself and ask him, what does industry think about prefabricated construction?
Yeah, so let me start by saying that whole intro, Vineet wanted me to sit here and do the robot when he was talking, but I told him no. So, yeah, I think, hey, if you to Vineet's point, I think if you look at the industry as a whole and some of the challenges we face, we need to start to look for areas that we've seen success, like precast, and how can we take a lot of those means and methods and apply them to cast in place. And look for other areas that we've done innovative things and figure out how do we continue to advance the ball. I think there's little pockets within the industry that we do well. Some things that we do at Barton Mello is if we have a tight site or tight schedule or things like that, oftentimes we'll take and prefab rebar cages, or we'll pre-build formwork and gang forms together, things like that. But that's not the type of innovations that are going to get us to where we need to go.
In the context of prefabricated construction in particular, some of the innovations we are seeing from a research perspective are occurring in robotization of the rebar cage manufacture process. So many of you might know that when prefabricating structural elements, bar bending and creating the rebar cage to perfect specifications is kind of a big deal. And from the work that I have seen and quite a bit of work that we have conducted here at the University of Michigan as well, this is a very potent area where robotics has significant implications. So the work we have been doing here primarily stems from BIM-driven robotics. So the idea being that if you have a detailed model of a rebar cage, how can you use that information to automatically extract that into instructions that can be used by one robot or a team of robots to fabricate the cages, both for longitudinal bars as well as the stirrups that tie them together. And because we are operating in a digital environment, much of this work can be conducted in the form of what is called a virtual prototype. So you can experiment with several different options before committing to one particular design that we can then build and test out in the physical world. So here we are showing an image of one contraption that originated in our lab several years ago. The idea was if we can create a modular aspect to the number of longitudinal bars that comprise a particular cage, and then use that as a way to swap out various designs using a team of robots, in this case 2 robot arms, and then have a collaborative process where you could draw in the longitudinal bars and then tie them up together. This was seen as a first step into robotizing the tedious rebar cage fabrication process. And our hypothesis at that time was correct because when we began speaking, Matt confirmed to us that this is indeed taking on speed in the startup arena as well as in the field. So why don't you tell us about that, Matt?
Yeah, I think it was interesting that as we're kind of preparing for this presentation, I get the Construction Dive is a publication. I get the weekly email from them kind of talking about what's going on in the industry. And as I'm kind of scrolling through the headlines, I see this article that Mark Cuban from the Shark Tank is giving seed funding to one of these companies that is looking at exactly this, right? So we're starting to see a lot of this stuff start to come to industry, which I thought was really, really positive. Yeah, so now we're going to talk a little bit about, things that we're doing in the field to kind of, what we say, plan our work, work our plan. Some of the challenges from a cast-in-place perspective on projects that we're challenged with is hey, things are always changing, things are always moving, we got challenging schedules, how do we control that? So our approach to that is we want to build what we call like Lego-type instructions. So I'm sure everybody in the room has gotten a box of Legos before, right? You got a bag A, bag B, you got instructions in there and it tells you exactly what to do. That's kind of our approach. So we want to look at things like site logistics, And how are we getting materials on and off the site? Where are things going to be staged? Where are our laydowns going to be? We want to control that environment as much as we can and take a lot of that variability out of it. How are we going to sequence the work? So we'll take, and use our BIM models that we're building and tie our schedule to it and be able to visualize and validate our schedules as we plan for our projects. Concrete and rebar modeling in-house. So all of our cast-in-place concrete that we do and all of our reinforcing steel, we model in-house. We want to be able to understand every bit and piece of that concrete, and we want to understand exactly what's going into it and again, control that. And then what we call lift drawings, or again, those Lego-type instructions. And then work packages. How are we making these into small digestible pieces so that we can look at some of those efficiencies that we're looking for. So this is just, again, a quick, I think it's a quick animation maybe. Yeah, so I'll kind of let this play. So this was a pursuit we were going after. And again, we want to understand every part and piece. Where are we going to put our cranes? How are we going to get material out? How are we going to sequence this? And we're doing this at the pre-construction level. So before we go and we're won the job, we want to make sure that we have the right plan of attack and we know exactly what's going to happen on the site and how everything's going to flow. So again, this isn't, down to the detail that we're going to build off of, but it's a really, really great starting point to be able to visualize and make sure that we have the right plan of attack and the right pricing associated with it. And then, I talked a lot about concrete and rebar. You can see this is a pretty complicated structure, but whether it's complicated like this or very simple, we want to put every part and piece in there. We want to model every piece of, reinforcing steel that you see in there, every embed, every anchor bolt, anything and everything that goes in there. We want to be able to capture and understand where it is, and then be able to give that location to our men and women in the field. And again, those Lego-type instructions, this is a pour on a project where we give them an isometric view and all the necessary information they need to be able to go on site, and it's not an entire job. We've already flushed through all those questions, building it in a 3D environment, and we've broken down into bite-sized pieces so that we can go then and execute it. And then lastly, we're going to give them a whole package of information that they need to go do it. So it's not just it's not just a 3D model. There's everything from schedule to how they're gonna charge their time, any safety concerns that we need to have. Everything is in this package so that they can then go and execute the work. So I'll talk a little bit about some industry challenges. Hey, if you start to look and think about why are we up here talking about robotics? So safety is our #1 priority. We want to send our people home the same way that they come to work. And it's very, very important to us. So, if you kind of look at the fatal four, as they call them, of safety incidents in the industry, it's falls, struck by, electrocution, and caught in or between, right? If we can start to use robotics to eliminate some of that risk, that's what we want to do. That's a huge advantage. Secondly, it's no secret we have an aging workforce. There's been such an emphasis on people who need to go to college. And while I think that's great, we're starting to see it within the industry right now. We're starting to see that we're not getting those young people coming into the industry that want to work the way that they do. So we got to figure out, as an industry, how do we solve that? And then, again, kind of in that same aging workforce is a trade number decline. Again, a lot of people are not wanting to get into the trades. So I'll play this video really quick. So this is a product that we've been partnering with construction robotics in. It's called the Mule. It's a material unit lifting apparatus. And originally it was designed for cinder block. We went to them and started to have conversation with them on how we can use it for things like formwork. So what we were able to do is customize and change the gripper so it can go and grip concrete panels. So this is, they kind of modified the gripper, and this is some testing they were doing with a local company in the state of New York. But the idea behind it is rather than have those guys pick those formwork up and carry them across the other side of the site, or figure out how do we, again, put people in harm's way, whether they're lifting or whatever. can we use a machine like this to enhance that?
So now we're going to talk a little bit about the third phase of a structure constructed of concrete, and that is retrofit or maintenance. And in that regard, we're going to speak first generally of the benefits of as-built reality or scanning as-built reality, and what benefits the industry has seen from that.
So from our perspective, I think how are we ensuring that what needs to go into the concrete is in the right location, and what measures are we putting in place to make sure that happens? So you got things like our pre-pour, our post-pour checklist. Laser scanning is a big one. When we do high-rise deck that have post-tensioning in it, the last thing you want to do is drill into one of those and have a cable shoot out the side of the building. It's not safe. It creates a whole lot of issues downstream. Again, now we have that laser scan, and because we're modeling all that concrete, we can start to bring those laser scans together with our BIM model and start to understand, hey, did we put these things exactly where they were supposed to go? Did we have everything covered? Again, it's just another QA/QC measure as well as an as-built. And again, we're using laser scanners, or we're going out there and shooting, a lot of those things, out on the site. And then, one thing that we've kind of again, as Vineet and I were trying to figure out exactly, what we're going to include in this discussion, one of the kind of internal debates we were having right now is things like anchors, So not just anchors, there's probably a lot of things that apply, but like how detailed do we get in that BIM model? Like what makes sense to include and what doesn't? And it's kind of that internal debate that we're having. So Vineet's going to take it from here and kind of show some of the research they've been doing.
So as an example, several years ago, we were approached by a railroad company, and the problem was that they built several concrete bridges that have the right of way for 2 railway lines, maybe going in either direction. But for whatever reason, right now, they build one set of rails with the second one to be built maybe several years later. And what they do is they leave specific anchor points on the unused side of the deck. The idea being 20 years later, we'll come back and start drilling the deck at those points and connect the second set of rails. The problem was when crews came to the bridge deck and started drilling such holes, they began to hit utilities, hit pre-stressing tendons, thereby affecting the structural integrity of the bridge. So what we were able to do along with the team at NIST is first understand how the industry currently solves their problem, and then introduce a measure of automation in this process of general maintenance and retrofit of concrete structures. So the way this is typically done is to leave wooden embeds in the concrete and then place concrete as you would. The idea being when you come back later, you are going to find out exactly where those embeds are, pull them out somehow, and then they serve as your anchor points. In reality, what happens is, and I'd seen this myself when I went on a bridge, 20 years does a lot to a concrete deck. It's not easy to find out where that embed is or even be able to distinguish it from everything else that's around it. And many times the workers who work there, they go by trial and errors. I think it is here, so let me start drilling, and the next thing you know, you hit something else. So based on this understanding, we developed a 2-phased process to try and address an issue like this. And I'm showing these 2 things here in this row here and the second row here. The first one uses detailed as-built scanning and modeling of the rebar and any utilities that you eventually don't want to strike or hit later on when the concrete is on top of it. So the basic idea there is you're going to create a model of the obstructions that will be under the concrete and essentially model that as a grid structure. And once there is now some new work to be done, for example, drilling on this surface, you are going to track the drill or the jackhammer or whatever device it is accurately, and the system can automatically tell you whether you are in a clear zone, one of these cells, or there is something else below. The second approach we also explored in this regard is to use a laser projected augmented reality. In other words, if you imagine this to be the surface of concrete and there is rebar under, if we have a detailed model and are able to georeference it with the coordinate frame of the bridge, we can project where obstructions lie under it so that now whoever is working can be cognizant of what obstructions are below. So this is just a very brief overview of the drill tracking system in perspective. So, what we have is a situation where we know where the utilities and obstructions are buried. We create a grid model of obstructions. From that point on, track in detail the end effector of the equipment that is to work there and provide real-time feedback to the worker whether it's safe or unsafe or whether any kind of lateral movement is needed. So let me now try to conclude with talking very little about some recent innovations in robotic concrete construction that we are foreseeing. We have heard a lot about innovations in 3D printing, so I won't speak much to that. And will only say that as researchers at the University of Michigan, we are very interested in this line of work, largely in collaboration with Professor McGee and the Fab Lab here. And last but not least, we also think that modular construction can take on a whole different shape and form, particularly through a project like digital Lego-inspired construction that is led by our very own Professor Victor Lee here. So we have just one more thing to show you before we conclude, and that's this short video about how we think industry is going to adapt to such changes. So I'll play that now.
Has long been criticized for stagnation and lack of progress. As an industry, we've been constructing buildings using the same means and methods for decades and lack the advancements that have been realized by the manufacturing industry, for example. We are finally entering the transformation. As a company, we're developing software that will design complex systems in seconds. We're investing in robots that can lay 1,000 bricks a day. We're planning projects so that we know where every material and piece of equipment is in real time. We're creating 3D models of projects with drones where the entire site is accurate to the inch, and putting technology in the hands of builders instead of just computer experts. And the Lift Build team are literally turning construction upside down. And it's just the beginning.
All right. So in summary and conclusion, I think as researchers and industry, we are both very interested in seeing where the trends of prefabrication versus on-site construction go, how far advanced mobile and adaptive construction robots can get, and are particularly keen to see what the potential disruption from 3D printing of construction methods come along. So I'll have Matt have the last word on this, on what he thinks about industry.
Yeah, so I found it fascinating this morning. I think, being from the industry, we often think about, kind of post to what was talked a lot about today. We get a project and we're assigned to go and figure out how to build it, on budget, within schedule. So it was very enlightening. You kind of saw that video from Bart and Mela to talk about, kind of our stance and what we think we have control of and kind of on the construction side. But again, I'm humbled and honored to be here. I really appreciate the opportunity to speak with you guys and really learned a lot. So thank you very much.
Thank you.
Okay, if I could ask all the speakers to join me up here, we'll have a brief panel discussion. I think Vineet has the lead. That's okay. Yeah, he's got a lead.
May I join you?
So I thought that was a particularly diverse group of presentations, so it actually kind of covered the spectrum of, you know, a lot of contemporary topics that we're very interested in, and I think was kind of the goal of the symposium. I wanted to kind of start out with a little bit of a question for Matt. You know, we have a lot of industry representatives here, and I think it's a big interest in how we deploy these methods to the construction site. And I wanted to ask, what methods of collaboration do you see between the construction industry and the academic research labs that work best? I mean, what are the modes of not only collaborating, but also working, you know, through a project, you know, whether that be funded research or just co-engaged research that has the potential to get some of these quite advanced, maybe far future ideas out to a construction site?
Sure. I think, quite frankly, it starts with, you know, opportunities like this. I think we're never going to get to where we want to go, like, you know, in silos. I think it has to be exactly what you just described. You know, I certainly don't have a recipe or don't claim to have a recipe to say this is exactly how it's going to happen, but, you know, hopefully with, you know, days like today where we can, you know, meet new people and have these discussions, you know, we'd love to continue to have the partnership with the folks at the University of Michigan and continue to do our part, certainly.
Matt, from your experience, what do you think sometimes is lacking from academia to make the collaboration really effective for you? What do we sometimes miss from the academia?
I would almost throw it back on you know, kind of industry. I don't think it's academia. Okay. I really don't. I think, you know, that curve that Vineet threw up, that says it all, right?
That was just a hook to try to make you say what you said.
Hey, I got it.
Thank you.
I got it. But yeah, I think, hey, we like to say at Barton Mello that we like to think different and we like to think innovative. So, yeah, it's a challenge, and we even, you know, experience that internally. You know, I always say two people, you know, people are afraid of change and afraid of technology. You know.
Well, there is the well-known so-called valley of death between R&D in academia and industry. Mm-hmm. Right? There's a gap there. Sometimes what we learn in our laboratory are ultimately not transferred into the market. So in construction, this valley of death is particularly deep, in my opinion, sure. Compared to other industries. What would you like to see from us, from academia, you know, in order to make that bridging?
Yeah, I think it comes down to communication and partnership, right? Like a lot of the things, just again through this opportunity with Vineet, a lot of the things that he was studying and talking about were really eye-opening to me, and I probably otherwise wouldn't have known about it, you know? So somehow we got to collectively figure out how do we communicate better, and you know, maybe we can host things at our office to have, you know, similar type discussions, and then vice versa.
Yeah, just picking up on that, Shadi, you mentioned something that really kind of stuck with me. It's something I feel like I've worked my whole kind of academic career working on, but it was really around the importance of engaging architecture and design early in the development of new construction processes. I mean, traditionally, architects worked at one end and delivered shop drawings, and someone else built the project, but I think at least in the academic end, there's been this kind of resurgence of interest in how the building gets built and really understanding that process. How have you seen in your work, especially with NASA, how that importance of keeping architecture at the table translates to the eventual success of the technology?
Yeah, I think a lot of architects, or the way I was trained at least, was that you design and then you assign materials and things like that, but that doesn't work anymore. I mean, for example, for me, I need to start thinking about material, in fact, designing of the material. And so all of it comes together. You need to think about the whole process and everything involved from the beginning. And so I think the use of BIM platform also, expanding that to include optimization, to include analysis, you know, to bring that too during the construction. Everything needs to work together.
Yeah, and I also think that touches upon what another thought I had was this idea of the disciplinary silos, which traditionally have kept these things stuck in the lab because we're all looking at our specific problems when, you know, the other fields could help solve that. I mean, does anybody want to comment on how that's changed, I guess, over recent years? Are we more siloed, or are we less siloed?
Well, I'll say something. I think that the project and the collaboration that Victor and I have been working on for the past couple of years is an example of where we took somewhat siloed research areas and we're able to cross that. It's in the same department, but I'm a geochemist. A couple of years ago, I didn't really know that much about cement materials. And I think in combining my experience in carbon mineralization with Victor's experience in designing new materials, we're actually able to optimize the production of greener, functional products in unique ways.
Yeah, unfortunately, I believe that in academia we have been much too much become silos and separate disciplines. So in our department, it's called Civil and Environmental Engineering, and Brian is in the environmental engineering side, and I'm on the civil. So it occurs to me that in many situations, civil engineers build the built environment, and the environmental engineers come back to fix the problem that we cause. And that, of course, is not the most efficient way. That was one of the origins of our trying to break that mold, to collaborate across disciplines.
You know, I might add, I'm kind of a fish out of water here, but even within NASA, after the moon landings and everything kind of went stagnant for a while, they tended to start siloing there as well. And you'd have a propulsion group and a stages group, and when they came together, lo and behold, the engines didn't fit on the stages, and so they started designing systems engineering to fix that problem. Now they're coming back around, and we're finding, for example, on my team, very multidisciplinary: robotics, computer science, planetary geology, mechanical engineering, and that's the only way a project of this kind of magnitude will ever be successful. So I have good feelings about that compared to, say, 15 years ago.
So I would even add that to your credit, and TN and other organizers of this conference, it's really a multidisciplinary platform that allows us to talk in a language, hopefully, that both communities can understand each other. And I see Sarah over there is also a very good example. She used to work, well, we used to work together on construction materials, particularly on the bendable concrete. Hi, Sarah. And I can see her from her talk that she's really very much into the built environment, the human building connection side. To me, I think this is a proper, the right direction to go. But we need much more of that.
Agreed. Well said.
So I'd like to open it up for questions from the audience. I see Arash is ready to go here.
I have a question for Matt. Where do you see good opportunities for augmented reality in construction?
I think there's a lot of opportunity. I think it's one of those technologies that it's new, right? It's kind of scary. So let me talk about kind of augmented reality and then virtual reality, kind of in tandem. Augmented reality, we're starting to see where there's companies that I've actually spoke to and had conversations with where they're starting to put like the HoloLens on to tie rebar. I've seen where they're doing like interior metal frame walls, bottom track and top track, and laying studs out all within the HoloLens. So I think there's opportunities there. Again, I think we're our own worst enemy sometimes, where we're just so afraid of technology. I think it's just over time, and it hasn't gotten better. You know, I don't want to sound cliche, but I say all the time, I don't know if I'm determined or stupid. I haven't figured out yet. But it takes a lot of that determination to constantly, you know, you try something and it fails, try it again with a different person. Sometimes it's just that right person at the right time, and you start to build off of those successes. In terms of virtual reality, we're starting to really look for opportunities where we can work with VR companies to do things like safety training. So when you have young people that come into the industry that have never stepped foot on a job site before, how do you kind of start to immerse them in that space and start to help them with those tools so that when they get out in the actual job site, they know what to look for. It may not be exactly how it looked on a screen, but they're at least a lot more aware than they were before.
So the question is simply for the Bard Mallow rep, with the modeling for the construction sequencing that you use to develop your proposals with, are you using the architectural Revit documents or BIM documents as a basis, or are you creating your own?
The latter, most of the time. Again, that's, I think, another challenge in our industry. Everybody's very hesitant to share that in a lot of cases. So oftentimes we're you know, I'm in a room full of engineers and architects, so I'm going to be careful what I say. You know, hey, I think sometimes in defense to the architects and engineers, their schedules, just like ours, are getting condensed, and their margins are getting less and less, right? So you're still asked to do the same amount in less time and for cheaper, right? So sometimes the quality of those models force us to use some of it and then build off of that, not use it at all, or they're not willing to share it. So we're forced to redo it from scratch.
So are you involved more with CMR or IPD in terms of project delivery, where you're collaborating with the architect and engineers earlier on, so you're part of that team?
Yep. So in those cases, yes, we're able to collaborate and get that. But in a typical, you know, rip and read kind of, you know, hard dollar bid job, it's usually the latter that we have to create our own.
Thank you.
Yep.
Thank you. I have a question about the NASA work. And I have a colleague that's doing something kind of similar to the lunar Crete, but so I should probably know the answer. But I'm wondering, especially with the 3D printing, where would all the energy come from? Like, I know you're not working on that, but I'm curious, like, it seems especially like sintering or something would need a lot of energy.
Oh, exactly right. You know, for years, anything we've done on the planetary surface has been solar power. And while techniques for solar energy are getting better, I think anybody who's seriously thinking about the kinds of activities that we're talking about, running 3D printing and building structures and then operating within those structures, NASA has for years developed and tested small nuclear reactors that have been tested, have been launched. There's always a public perception about the safety of those, but within the agency, I think they're very comfortable with the use of them, and nuclear power would be the way we would, it would be isolated. We would probably actually 3D print a berm or a container that the reactor would be located in. At least that's one of the rationales we've used for 3D printing. But I think nuclear power is the way to go.
A question for the NASA team. As I understand it, many of our marvelous technological developments were spurred by the space program and particularly by the race to the moon. What are the chances that history is going to repeat itself here, and that you folks are going to use the moon and the Mars as the way to show us the way the future is going to be here on Earth?
So the motivation to go to the moon the first time was political. But it was sufficient to get the country behind it, at least for a short amount of time. But even before the first landing, public perception was already turning against the expenditures. NASA is its own worst enemy, I think, in terms of self-marketing. You know, everybody thinks Tang and Velcro. I mean, it's sad. The technology development that took place to go to the moon and since then is absolutely remarkable, and it's prevalent everywhere. Anything, you know, when farmers are out evaluating their crops and they're using satellite communications to evaluate, that was all developed for the space program. The miniaturization of electronics was all driven by the space program. so if you think about it, I mean, if you really get into it, there's more than enough technological motivation to go back. Because now, you know, if we're going back, we need to go back to stay, which means the technology advancements will be even more significant. They have to be, almost by definition. So, did I answer your question?
Yes, and my comments were entirely positive and affirmative, and I'd just like to thank you for leading the way.
Oh, thank you. I'll tell all my friends.
So now I'll ask the dystopian question, since I hang out with architects too much probably as an engineer. In the context of CO2 sequestration, I'm curious about the net balance, first of all, in the bendable concrete. This is more specific to that project. But then if and when we go to the moon, will it be because we haven't sequestered enough carbon and we just need a new place to live? Or are we really motivated to go there before that? That's more like a hypothetical.
Well, that's a really good question, and I don't have the real technical background regarding carbon sequestration to address that part of it. But I believe the reason to go back to the moon is a more philosophical one of we're humans, we need to explore. I know it sounds like motherhood and apple pie, but I think the majority of people who work in the space program really feel that way. And we get wrapped up in the bureaucracy like everybody else does, and it's frustrating sometimes. But the moon is an excellent place to learn how to live. I mean, there are those that would argue that we're going to destroy ourselves in a number of years, and we have to be able to be living somewhere else by then. I don't know about that, but I do feel like we need to have, we need to be able to live on other planets. I think the moon is the next logical step. If we can live on the moon, it's easier to live on Mars. You got communications delays and issues, but the moon is a much harsher environment to live in than Mars is. Whatever the ration, we know that, for example, for deep space missions, if we can extract oxygen from water, oxygen and hydrogen from water on the moon, and put that in low lunar orbit, then it's a logical way station to refuel on our way to somewhere else, Mars or somewhere else, and it really reduces the impacts of launch mass on Earth. So.
Mike,
that's my thought.
Can you repeat your question on the carbon sequestration aspect?
Well, yeah, I could rephrase. So on the sequestration part and the content, how do we address, and you are doing a great job. I'm very excited about the work. It obviously addresses the things that we talked about this morning in terms of reinforcement and sequestration. But one of the sort of mental experiments I always do about sequestration in concrete is when you make concrete, half of the emissions are chemical emissions and half are from the heat to make the cement, right? And then when carbonation happens, it's actually the chemical part kind of coming back in, right? So in this dystopian scenario I set up, one of the experiments I always think about is if we all just stopped having an industrialized society, how much CO2 gets sequestered by the buildings just because they're sitting there reabsorbing all their CO2. And so for me, that also points out the fact that when you do carbon accounting, if you guys are still making new cement to make your cement, then you're not really sequestering, right? So the new cement doesn't make sequestration. It's actually only the cement we've already made that can sequester, but it can never make up for all the emissions that it originated with. So it's more of like I always have this question of how do we account for across the whole time scale of when things get emitted and when they get sequestered. And, yeah.
So there are trends in the research community and progressively moving into practice of greening the binder, replacing the Portland cement, for example, by pozzolans, and further, as I pointed out earlier, by, for example, LC3, which is a material from limestone, calcine clay, and limestone mixed with Portland cement. So those will be effectively reducing the embodied carbon in the material. And then plus the carbon sequestration, we are not quite there yet, but the dream is to eventually get to carbon negative concrete. I believe that's what you are shooting for, but yeah, we're not quite there yet, so that's what we're aiming at.
And one of the aspects, potentially thinking about life cycle emissions, is if you have more durable materials, or you have materials that you can reconfigure to construct new things, then you can close the loop. Right now we build a building, and when we want a new building, we just knock the old one down and put a new building in with all new materials. And so if you can move away from that, where you have reconfigurable concrete structures, or you just have materials that don't need to be replaced as often, you can, at least relative to current state-of-the-art practice, have much lower life cycle emissions.
Yeah, this point is particularly important in transportation infrastructures, roads and bridges. Much of the carbon and energy footprints occurs in the operations and maintenance, particularly the repair activity, as opposed to the carbon or energy embodied in the material itself. So if we can make our infrastructures with materials that are much more durable, extending service life by doubling or tripling or even quadrupling, we would be able to reduce a lot of the carbon footprints. So in my mind, is reducing carbon in our built environment is not just a matter of greening the material, but it's actually every stage of the life cycle of our infrastructure, from material to construction to operations and maintenance and end of life. Regarding the end of life, I might just add that Vineet was showing very quickly a picture of the Lego type construction. So that's an idea that we borrow from Lego toys, and Lego toys, kids play with it. One day they make a train, the next day they disassemble it quickly, rapidly, and then reassemble it into, let's say, a building. And so this is totally rapid assembly, rapid disassembly, and reconfigurable. And that allows us to have full reuse, not just recycle. Recycle generally means destroying the material and downgrade it. But there is a possibility that we can reuse those Lego blocks. Now, one of the criteria, of course, is normal concrete. It's impossible to connect them by dry joining, because if you use nuts and bolts, they fracture at the joints because the material is brittle. But ECC offers that possibility that we can do dry joining and rapid joining and disassemble and rapid reconfiguration. So those are the kind of things that we are thinking about. We are not quite there yet, but those are ideas that we are toying among ourselves. We're working hard on those.
All right, my question is in regards to the ductile concrete. And I'm just curious, you said that ECC could, once you bend it, it cracks at 15 micron thicknesses, and then as it is exposed to water and atmosphere, it heals itself. So I'm just curious if that, the more that happens, does that disintegrate the process? The more it cracks and the more it heals, is there disintegration in the process, or is that a perpetual retractive process that it could cyclically occur? And basically I'm asking about the longevity of the ductile concrete.
Yeah. So I think you are asking about the longevity of repeated healing. Is that yeah? So we do not have enough experience to say that it will be infinite cycles of self-healing. But we do have experience in the laboratory of observing self-healing under multiple cycles. How much it will heal depends on the level of damage and the type of exposure environment. For example, just humidity compared to wet and drying, or just total immersed are different. So the answer is a little bit more nuanced. It's not so easy to reply. But basically, we expect that at least for common normal usage, multiple cycles of rehealing is feasible.
And one of the things to keep in mind, too, is it's not just, did it regain its original strength? But when you have those cracks form and then heal, you regain the low permeability of the matrix, which effectively can prevent the ingress of other, chloride or sulfate materials that are going to be have a negative impact on the longevity of the material. So it sort of helps in both those ways.
So I'm kind of curious if, with the self-healing concrete, is the material of the self-healing mechanism you're using dependent upon the environment, or does its reactivity or performance just depend on the environment? Would you change, if you knew you were operating in a dry environment, would you use a different material than if you were immersed?
We can, yeah.
Okay.
So in general, we can tune the material. So one of the characteristics of ECC is that it's not just a single material, but it's more like a family of materials with the common denominator that they are all ductile, like metallic behavior under mechanical loading. But the exact composition depends on what application and what type of exposure environment. So for example, there are versions of ECC that are deliberately designed to be very lightweight. Our students actually use it to build concrete canoes, which are extremely lightweight. And then there are versions of those that are built for very rapid hardening, high early strength, and so on. So we can also tune the composition to the requirement of if we are expecting a certain different type of environment, we might be able to tune that.
Very good, thank you.
So if there's no further questions, if there is, we have time. Oh, okay.
Just a quick one on operational matters. There's all this vertical association with things we're familiar with, whether it's materials or systems, but what about lateral? And I'm thinking more in terms of AR and VR in the aeronautical industry, mechanics. I mean, they've been using these techniques very effectively. Do you go across and have a look at what they're doing?
Yeah. So short answer, yes. I think there's a lot to be learned, for sure. Daiquiri is one company out there. They had the smart hard hat that they were trying to get into the industry, and then they came out with the goggles, and then last I heard that that went away. But yeah, I think there's a lot to learn from different industries, certainly.
Thinking about training.
Yeah.
Okay, well, we'll break for coffee. Please join me in thanking our presenters one more time.